Okay, chapter 17, 28, 30, and 32. So we're talking about shooting arrows at a target, and the probability for this one archer of a bullseye is 0.8. They're taking 200 shots. Now, is this a Bernoulli probability? And then furthermore, is it a normal? Can we use the Bernoulli probability in a normal model? So number one, it's a yes or no question. Either the archer hits a bullseye or the archer does not. Two, the probability of a bullseye is constant since 200 is less than 10% of the archer's total number of shots. If they do 200 one time, we have to assume that the archer has done many thousands, probably tens of thousands of shots. Three, we have no reason not to assume that the shots are not independent of each other. We're not told anything that would indicate that the shots are not independent. So that establishes that we have a Bernoulli event, or Bernoulli trials. That is, each shot at the target is a Bernoulli trial. Number four, the next two preconditions will establish whether or not we can use this Bernoulli probability in a normal model. And in order to do so, NP, which is 0.8 times 200 equals 160, must be greater than 10, which it obviously is. That also, by the way, happens to equal the mean, NP being the mean, for a binomial probability. And NQ must also be greater than 10, and NQ, which is 0.2 times 240, equals 40, that's also greater than 10. So not only do we have a Bernoulli event, but we can use it in a normal model. So we will state the mean and standard deviation. The mean, as we already stated, is NP. That's 160. And the standard deviation is the square root of NPQ, which is 5.66. Now they asked us to spell out the normal model. So 160 is in the middle, and then you would add plus 5.66 plus 2 times 5.66 plus 3 times 5.66 for the different, for 1, 2, and then 3 standard deviations. This is minus 1, minus 2, and minus 3. So it'd be minus 1 times 5.66 minus 2 times 5.66 minus 3. And so again, it's a 68, 95, 99.7 distribution of probabilities. Now, the next question is for D. What's the probability the number of bullseyes is less than or equal to 140? So we're going to use a normal model, and so we look at the mean is 160, and we're interested in the probability of 140. We'll do 140 minus 160 over 5.66. And the z-score is negative 3.35. And so the probability, that's a big z-score, which means that we have a very low probability. The bigger the z-score, the further out in the tail. So the probability that the bullseyes are less than or equal to 140 is less than 1%. Now you could also just do this in the binomial model. Since this particular question, what's the probability the bullseyes are less than or equal to 140? We could do second and vars and binom CDF B. So N is 200 and P is 0.8, and we're looking at 140 successes. So X is 140. And this probability is similar, very close to the probability we got with using the normal model, but they're both very, very small. Okay, 30. It's another discussion with the frogs. This time we're going to have the sample size for frogs to be 150, and the probability that the frogs have the particular trait that the scientist is interested in is 0.125, or 1 out of 8. So the average they asked for the average of the standard deviation. It's NP. It's 150 times 0.125, which is 18.75. Sigma is the square root of NPQ, which is 4.05. Now, can we use the normal model? Well, it's yes or no. The frog has the trait or it doesn't. The probability of the trait doesn't change since n equals 150. 150 frogs is less than 10% of the frog population. There's probably millions of frogs. 3, there's no reason not to assume the frogs are not no reason not to assume the frogs are independent of each other. Okay, so number 4, NP equals 18.75, which is greater than 10. And NQ is 150 times 8.75, which is 131.25, which is also greater than 10. So it's okay to use the approximately normal model of 18.75, 4.05. So the question C is, what's the probability of getting 22 frogs or more? So we do 22 minus 18.75, 4.05. Z-score is 0.8025, and so that's going to lead to a probability of 0.211 using normal CDF. So let's just run through the normal CDF. That'd be second, and then vars. Normal CDF 2, and then we're going to do 0.8025, 99, going all the way to the end of the tail, and it's around 21%. So we're going from 0.8025 here to 99. That's around 21%. So the probability that 22 frogs or more have the trait is about 21%. Now, 21% is like 1 out of 5, which means you could get a sample of 150 frogs in which 22 or more have the trait. This could easily happen by chance. Okay, so it doesn't indicate, since this could happen randomly quite easily, 1 out of 5 is not an improbable event, then we do not consider this to be evidence that the proportion of frogs that contain the trait is anything other than 0.125. We still think it's 1 out of 8. We don't have any evidence that it isn't. Okay, 32. No-shows. Probability of a no-show is 0.05. The plane holds 275 people. So we're going to analyze this. Is it Bernoulli? Yes, no. Yeah, you show or you no-show. 275 is certainly less than 10% of all airline tickets. No reason not to assume the passengers are independent. And then furthermore, NP equals 0.05 times 275, which is 13.7. We're doing this like in terms of no-shows, which is greater than 10, and NQ is 0.95 times 275, which is 261.25, which is also greater than 10. Okay, so we're going to use a normal model for the no-shows of 13.75, 3.6142. Now, if the no-shows are 9 or less, then the plane is overbooked, and that's the question that's being asked. What's the probability that the airline will not have enough seats? You won't have enough seats if the no-shows are 9 or less. Okay, so the z-score is going to equal 9 minus 13.75. That's negative 4.75 divided by the standard deviation of 3.6142. Okay, so let's see what that is. Negative 4.75 divided by 3.6142. So the z-score is negative 3.14. And so we're going to go to negative 99. So we'll do a second and vars, normal CDF2. And remember, it's always from left to right. So I'm going to go negative 99, comma, and then I'm going to put in that answer, that z-score. Okay, and so the probability that the z is less than negative 1.314 is approximately equal to 0.094. Okay, so there's like a 9.5% chance that they'll be overbooked. That seems pretty high. Now, you could also do this with binomial CDF, which would calculate the probabilities from 0 to 9 and add them all together of a 0.05 probability out of 275. So we'll do a second and vars, an arrow up to binomial CDF, 275, comma 0.05, comma 9. Now this answer will be slightly different. It's 11.5%. Now, I'm not going to get into why they're different, and either method is okay. Either method is fine. All right, so that's those two problems, 28, 30, and 32.